So in this problem, we have two random variables x and y, where x and y are jointly distributed according to the density function fxy of xy, which is equals to 6x when x and y belong to a shaded region, which is shown in this figure here. And we define a new random variable z, which is x minus y, and what we're required to do is to find the probability density function of z, which is fz of z. So in these sort of problems, we use the distribution function approach. That means we will begin with finding the distribution function of z, that is capital Fz of z, and then we differentiate this to obtain the small fz of z, that is the probability density function. So the distribution function is by definition the probability that the variable z is smaller than some value z, which is arbitrary, and this can be written as the probability of x minus y being smaller than z, which turns out to be the probability that y is bigger than x minus z. So the distribution function fz of z is to find the probability that y is bigger than x minus z. So let's draw the line y equals to x minus z and figure out where y is bigger than x minus z. So the line x minus z will look like this if z is positive. So the moment z is positive, the y-intercept becomes negative and we will have minus z here. And if z is between -1 and 0, then the line will be here. So this is the line y is x minus z when z is between -1 and 0. And of course, if z is less than -1, the line will be here. So for each of these cases, we need to figure out what the probability of y is to be bigger than x minus z. Of course, this case here and this case here is trivial because when you look above this line, for this line here, all the density is above this line. So the probability will be just 1. And if we consider this line here, there is no density above this line, so the probability will be 0. So the only case which is interesting for us is this one, where z is between -1 and 0. So the probability that y is bigger than x minus z means that we look above this line and we see that this is the region where basically y is is bigger than x minus z, and the density is defined for x and y. So computing this probability is just integrating the density over that shaded region. So it will be a double integral of the density, which is 6x. And because this sort of region is easier to integrate over y first, so y will be x minus z here, and y will be 1 here, and x goes from 0 all the way to this point here. So let me just write this here. Y is x minus z here, and y is 1 here. Sorry, y is 1 here, and this point here corresponds to the x being equals to, so that the line is y equals to x minus z. So if y is 1, then x is z plus 1. So then the integral turns out to be dy dx, and y was from the line x minus z all the way to 1, and x was from 0 to z plus 1. So the next step is just computing this integral. The inner integral is simpler because there is no variable there. So it will be just 6x times 1 minus x plus z, and then dx, which turns out to be 0 to z plus 1, 6x minus 6x squared plus 6xz dx, which will be 3x squared minus 2x cubed plus 3x squared z, and the limits are from 0 to z plus 1. So this turns out to be x squared 3 minus 2x plus 3z, and the limits are from 0 to z plus 1, and then we can write this as z plus 1 whole squared times 3 minus 2z minus 2 plus 3z, which will be z plus 1 whole squared times z plus 1, and that turns out to be z plus 1 whole cube. So the last step here is to take the derivative of the distribution function to obtain the density function. So that means fz of z is the derivative of the distribution function, which is d over dz of z plus 1 whole cube, and it turns out to be 3 times z plus 1 whole squared. And z here will be from -1 to 0. And that's the solution.